Imagine a robot arm trying to pick up an object from a table. It reaches its gripper to the exact same spot every time, but have you ever noticed that the arm itself might move in slightly different ways to get there? One end-effector pose can indeed have many solutions due to a fundamental concept in robotics called inverse kinematics, particularly when the robot arm has what is known as kinematic redundancy, meaning more degrees of freedom than strictly necessary to reach a specific point in space. This phenomenon arises because an end-effector's pose, which describes its position and orientation in three-dimensional space, requires 6 independent parameters to fully define it. A robot arm, however, can have many more degrees of freedom than these 6. For example, a typical industrial robot might have 7 or even more joints, each representing a degree of freedom. When the number of joints exceeds the required 6 for a general pose, the arm is kinematically redundant. This means there are multiple combinations of joint angles that can achieve the exact same end-effector pose, much like you can touch your nose with your hand in countless different ways by moving your shoulder, elbow, and wrist. To manage these multiple solutions, robot engineers employ various strategies. They typically use optimization criteria within their inverse kinematics algorithms. These criteria help the robot choose the most suitable joint configuration from the many possibilities. This could involve selecting a solution that avoids obstacles in the workspace, minimizes the energy consumed by the motors, keeps joints away from their physical limits, or optimizes for speed and dexterity. This concept is closely tied to the idea of a robot's configuration space versus its task space. The configuration space describes all possible joint angles, while the task space describes the end-effector's position and orientation. When an arm is redundant, a single point in task space maps to an entire manifold of points in configuration space. This is often solved using advanced mathematical techniques such as the Jacobian pseudo-inverse, allowing the robot to perform secondary tasks while maintaining its primary end-effector pose. Understanding that a single end-effector pose can have multiple kinematic solutions is not just a mathematical curiosity. It is a powerful design principle that gives robots incredible adaptability and versatility. This redundancy allows robots to navigate complex environments, work around obstructions, and perform intricate tasks with greater flexibility and efficiency, ultimately making them more robust and capable tools in a wide array of applications.
If you love robotics, like, subscribe, and keep building with us.